Okay, I think we can get started. So welcome everyone to our Metaverse class. It's the 9th week, and with this week we're talking about synthetic realities. We have two special guests today here. We have Andreas Blattmann and Rombach. Both are PhD students, I think, still at the Ludwig Maximilian University in Munich. And they're also researchers at Stability AI, a company who we probably all know from Stable Diffusion. But recently, there's a lot of other things that also get published from this company. And I'm really happy to have Andreas and Robin here because when you search a little bit about the backgrounds of Stability AI, you will find their names pretty prominent because they invented the paper and the ideas around the models and the technology that lead to stable diffusion. So I'm very, very pleased to have them here in the class today. And that's my first part of the introduction. So maybe you can tell a little bit about yourself, what you want to add.
Sure. Sorry. Thank you very much for a nice intro. Pleasure to be here. Yeah, let me just start, and then Andreas can go second. Yeah, we are both PhD students, that's right, at LMU Munich in Germany. Close to finishing our PhD. It shouldn't be long, like a few months, hopefully. And yeah, we've been working together actually for a while. So we met in the PhD back at Heidelberg University when our group was still in Heidelberg, also in Germany, and then started to work together on generative models, mostly image models that were trained in various latent spaces. So previous work was that we did was VQGAN and then ImageBART and stuff like this. So all kinds of generative models in like discrete latent spaces, continuous latent spaces, and so on. And at some point, when diffusion models popped up, I think 2 years ago, we started to do like the obvious thing, like extending our work in latent space to diffusion models, which ultimately led to our work on latent diffusion. And yeah, this is kind of the background paper for stable diffusion. Yeah.
So we do have a very interdisciplinary audience. There's designers in the audience. There are HCI researchers. There are AI researchers. There are all kinds of perspectives, which makes up the Media Lab. So can you tell us a little bit, or can you explain us a little bit what stable diffusion is and what, from your perspective, what's the interesting parts of it? What that separates it from what else is out there?
Andreas,
Goodbye, Robin. Do you want to answer?
Go ahead.
Okay. So hi, also from my side. Nice to be here. Thanks for having us. So yeah, Robin already said like lots about latent spaces actually, and in my opinion, this is really the difference between stable diffusion and other approaches. But first of all, the stable diffusion, as we might all know, is a generative model which is conditioned on text inputs, so we can input a text, and the model renders a hopefully nice image. And it's a generative model because it models the missing information from that text prompt to the image. So we can imagine a text prompt like bluebird, and we can as humans naturally imagine 1,000 instantiations of this image, right? Bluebird could sit on a tree, could fly through the sky and whatever. So, and this ambiguity is basically modeled by this generative model. Actually, it estimates a probability distribution or density. And yeah, there are a wide variety actually of like different architectures or probabilistic models implemented with different neural networks as architecture you could imagine with this. And Stable Diffusion is as the name suggests, diffusion model. These have been like within the last 2 years, these models have been extremely or have got extremely powerful. And by now they're the like for image generation, also I think for other domains, they are state-of-the-art models. So we have a couple of other architectures, as I already said, but these are like for images, they work best, although they have some drawbacks, which might come to speak later. And yeah, so shall I like elaborate a little bit more about like how exactly they work, or is that enough? I don't know. Like
I think that would be my next question. Yeah, like what makes the diffusion model so powerful? What is it that suddenly everyone is like that big jump that we see? You know, we saw big jumps throughout a couple of different products, so to say, out there. I think the software that you put out is differently seen, and we will talk later a little bit more about the open source part. But what is that jump? Why is that happening right now? Why do you say diffusion models are so powerful?
Shall I answer, Robin, or do you want? Okay, I think there are a couple of reasons for that actually. Yeah, maybe I'll mention the first 2 or 3, and then Robin can maybe add something if he wants. So first of all, they have for images. I said for images they are like state-of-the-art models. For text, not, because of like a couple of things, I would say, or a couple of this has a couple of reasons. So for images, they being implemented with the architecture, they are implemented or in the architecture with we use a UNet. There are also by now other approaches which might be similarly powerful, but actually the probabilistic model offers you a wide variety of different architectures how to implement it. So you always have a probabilistic model, and you have your backbone, your neural network, which implements some or estimates some quantity mostly. And diffusion models, that formalism leaves you very, very much like flexibility for designing that architecture. For other generative models, that's not the case. For instance, if we take normalizing flows or something, we are restricted. They have to be invertible. So if we want a neural network which can be principally any function, this restricts us a lot because we can only use bijections, which is like a quite narrow range of functions. And like principally, diffusion models offer or allow you to use a wide range of like architectures. And for images, we have like found some particularly powerful, I would say. And this is one part. The second part is they, as opposed also to other, this is like due to the probabilistic model, diffusion models do not generate a sample in a single step. So, or in general, generative models are like, they map from a simple distribution, which we can somehow parameterize or where we can sample from, to this unknown data distribution, which we want to approximate in the end. And in between, there is this model, which should in the end create samples from noise, as we all, or as many say. And some architectures, such as generative adversarial networks, known as GANs, you might also heard of those. or also being variational autoencoders, normalized flows. Others are doing this in one step. So, I mean, we can imagine the way from noise to data is quite like far, or it's quite a distance, right? And other approaches are doing this in one step. Diffusion models divide that way by applying an iterative noising process. So they basically, like, this is in the training procedure, they add tiny amounts of noise, like iteratively add tiny amounts of noise to the data sample. And if you do that like on and on and on and on, you will reach a stationary distribution. And we know we in the forward process, we fix this noising, the form of the process, we know it, such that we know at which distribution we arrive in the end. And this is, surprise, surprise, a standard normal, which is like often used as a prior. And diffusion models then learn to invert that process. And I said it's iterative. So we add tiny amounts of noise in each step or in many steps. Can also do this in continuous time. The model then at one training step, it learns to invert exactly one of those intermediate steps. We condition it on the step such that the model knows, okay, I'm at this point in between noise and data. And we see that we basically subdivide this really, really difficult problem from noise to data in many, many small steps, which obviously should be a little bit easier. Another point is we have parameter sharing. We always use the same model for these steps. Theoretically, we could use, like, if we have 100 steps, we could use 100 different models, but we always use the same model such that like we might be able to transfer knowledge from one step to the other because we always use that same model. We might be. But this, I think this iterative thing is really a useful property. We see it also by looking to the text domain, where we have autoregressive transformers, which are there like extremely powerful state-of-the-art models. And these are also iterative models. They generate not like it's a little bit different kind of iterative, but also those are really iterative models. And for both, maybe as a third part, then I will lead to Robin, which you can follow up maybe. They are like, they have an extremely stable training objective, which is like they come up with some estimates of the, or you can basically train them with maximum likelihood estimation, which offers us a really nice and stable objective. For diffusion models, you have a bound on the likelihood, and for transformers, autoregressive transformers, you even can do it like exactly. But yeah, and this is one reason why they have really nice scaling properties. And I think on that, Robin can maybe like say also a little bit. I think he fits in here quite well.
Yeah, sure. So we had iterative refinement. I think this is like one of the most important ingredients for scalable models right now. Either, as Andreas said, autoregressive transformers or diffusion models. And something that is particularly important for diffusion models is actually that this is something inherent to image data actually, and to video data and natural data. So there's in this natural data signals, there's lots of redundancy that like high frequency details that we as human observers don't really perceive, right? So, and if our goal is to synthesize new media, to synthesize new images, new natural data, then we actually don't want to waste model capacity on synthesizing something that is in the data but that we don't perceive. And diffusion models, they actually offer a very nice formulation that kind of weighs down the contribution of stuff that we don't perceive. And
So it's kind of like a cleanup step, an automated cleanup step in there.
It's more like a natural way to focus the model towards what is important to learn.
Okay.
I would say. And this is also very related to this work on latent space modeling that we have done. So these are kind of two approaches to the same thing. So with that latent space modeling, it's kind of the same motivation. We have like high dimensional input data, images, which are very hard to model because of the high dimensionality, even for a very expressive model, right? And using that insight that there is lots of information in the data that we don't need to generate or synthesize in the end, we can say, hey, can we learn a representation of that data that is more easy to model with the generative model? And this is usually done with that latent space approaches, like autoencoding approaches that are trained in combination with a adversarial approach. And this kind of ensures that the data that is reconstructed from that latent space is still looking like realistic data, but a lot of that high frequency redundancy is removed from the latent space.
So it sounds like
these are kind of two orthogonal approaches to the same thing. Latent diffusion kind of combines them.
Okay, so it sounds like, so I'm not an expert in the field, which is an interesting interview to have here, or interesting conversation to have. So it sounds like there's a kind of an abstraction or a focusizing process going on, something that crystallizes the information out. And then in the second step, when you go from the noise back to the image, you have an iterative process that also makes the process more potent. So is that where stable diffusion separates from other diffusion models? Like I've learned in the last days, I listened a couple of podcasts and so on to learn a little bit about what you do. And apparently your software runs on machines that anyone can have at home. So it's democratizes this technology. And are these two steps the reason why that is possible?
Yeah, I think the main difference to these like vanilla diffusion models is that we actually do run in this latent space of reduced dimensionality, which makes computation more efficient. And the way that this latent space is learned, it's kind of this autoencoding architecture that I mentioned earlier. And this is, you can decode an image from that latent space in a single step. This is fast, kind of cheap also, and you don't have to do the iterative process on the data domain itself. And then we just have to do the iterative denoising process on the latent space. And because the latent space is of reduced dimensionality, the computation is kind of efficient.
Does that mean, do you shift compute time from the generation into the training? When you say you bring it into the latent space and then from there the next step is less compute intensive, is then there a bigger computation step in the training?
Yes, so we have to pre-train this autoencoding architecture, but it's actually not too compute intensive to do that. I think something else that's worth a note is actually that by doing that we introduce some kind of error, right? So we introduce an upper bound on the quality that we can actually achieve with the generative model. If we would train in pixel space directly, we could achieve pixel perfect models. And by doing that latent space approach, we kind of trade the very, very highest quality results for compute efficiency. But because of that, all that redundancy that is in the data, this is something that is, I would say, worth paying actually, because what you lose is not too much compared to what you gain. And you always, like, if you have to compute, like approaches that work are you could do the latent approach and then take a pixel space diffusion model and refine your generated image to smooth out like even the last details that you're not satisfied with. This is expensive then, but if you have the compute, you could do that.
And still, I mean, in this case, you would have to take only a few steps with this pixel space model then, because you would condition it on that already really good sample actually. No.
So how did you come up with that? I mean, there's a couple of probably master students, PhD students in the room. They all know these moments where you try something for so long and it doesn't work.
Yeah, it's a good question.
Somewhere in a shower in the morning or something, you're suddenly like, oh, you know what? There's this idea. Like,
yeah, actually it was like Andreas mentioned normalizing flows earlier, and all this latent space modeling work, it started with normalizing flows. So the goal was can we train normalizing flows to generate high quality image data, which is super difficult. And
this was just like for practice reasons, right? So it's just not possible on the image space.
Yeah, exactly. So, and also the architecture that we used for implementing the normalizing flows at the time, it's called coupling layer. It's not too expressive actually, and to make it work, we already came up with one of these autoencoding approaches. For those, the autoencoder did actually learn like a single vector representation, and then we would train the normalizing flow on that vector representation. And this I really remember that like the first time I implemented that, I think I used some normalizing flow implementation by Andreas actually, and it was just plug and play. You could just plug it into the pre-trained model and it just worked on some, I think, portraits of dogs or something. That's the data and it looked really nice. So yeah.
So you did have a Heureka moment.
Yeah, that was
that worked.
Yeah, maybe that was one of them.
So this was how it started actually, and the next part was, I mean, Robin can tell much more than I can about this work, but I of course I also like know about it. The next thing was like taming transformers, which is also like a really big deal these days. I would say it's by now actually. I just realized that like 2 weeks ago, for me, it's really essential work, and others who just like came up to that field in the last year or something, or 1.5 years, they might not even know it, but it's really important. Then like Robin and Patrick, I was not particularly involved in that work. Shifted towards like other probabilistic architectures and came up with those autoregressive transformers, which were also like known to be extremely effective for text. But on images, again, it was like a computational thing, because you have, for them to work on images, the naive approach would be to just like subdivide your pixel grid into like into discrete tokens or something, and just like do this autoregressive model over the entire image, which is extremely hard because your context length, or like the length of the sequence you want to like model, is like it scales quadratically in memory, and you cannot train such a model like with somewhat large batch size, or not at all on high resolution images. And there again, this two-stage approach with the latent space offered a nice resort, because you could just again train an autoencoder which maps onto that compressed latent space, which has a far lower dimensionality. Then you can train this model there. Plus, the bonus there was you didn't have to go that far down for normalizing flows. You really have to compress really much, and you always face, Robin mentioned that earlier, this trade-off between compression and perceptual quality of your outcome of the autoencoder. This is the inherent trade-off. And for like autoregressive transformers, there was also like you didn't have to compress because of the model. You didn't have to compress as much, such that the autoencoder, which, as Robin also said, is the upper bound on the overall performance of your combined autoencoder and generative model, is like better. It's just yielding better results, and it's more general. Can be applied to like much wider data sets or more diverse data sets. And yeah, so this was already cool, but it was still like limited by this memory issue, and you couldn't like have any size of latent space. And this is then the difference between this taming transformers work, which I recommend everyone like who reads papers in this area. I recommend to reading that, because it's really a really nice paper, I think. And with diffusion models, so this was what you shifted towards then. And there we were actually able to investigate this trade-off of like perceptual quality of your reconstructions of the autoencoder versus computational efficiency of your latent space. And this is what we actually did in the paper. We just like trained many models, different latent space dimensionalities, and just like evaluated, okay, where would a diffusion model, in which regions would a diffusion model perform best? And this was how we like investigated this nice trade-off, which also stable diffusion obtains in between like perceptual quality. And you see sometimes for domains such as human faces or fingers, we are really specialized at. So we are actually really good at perceiving them. This is why it always comes to our mind, or when looking at those. This is why they're still not perfect, but the trade-off is really good because it is so efficient, right? So samples are in general quite nice, I would say. And yeah, the model is just, as you said, computationally very efficient.
Interesting. I listen. There are two things that I hear out of here. There's the one part, the efficiency, that that really brings some sort of democratization, and that's actually my next question there. But there's also another aspect is about you lean onto knowledge that's has to do with text, and you lean it into the image. When we prepared some of the question, there were also the question: could you use this latent space and could you use that also for music? Is it something that you could also transfer in that territory?
Yeah, I think that makes a lot of sense. There actually is an audio LDM, so audio latent diffusion model.
And I think at the really start, when we like started doing this, there was, do you remember this symbolic music generation with diffusion models, Robin?
Yeah.
This was also really, it is basically also latent diffusion, but applied to music generation. It is really like, I think it's came out early in 2021 or something.
But the motivation is a bit different for this one, because they learn like map from like the symbolic notation into some continuous latent spaces.
Yeah.
I think the other way, the natural way would be, okay, you have some audio data, some raw audio data, and you encode that into a latent space and remove high frequency stuff. That is not too important, but I don't know, that requires some domain knowledge about music, I would say. So yeah. Actually, maybe to add to the transformer and latent diffusion story. So the main reason we did this was that GPT-3 came out, and then transformers were all the hype. and we just wanted to implement something with transformers. So this was very obvious for us to do. Just use the architecture for something and get to use for the architecture. And then when we did latent diffusion, this was kind of the third round or third approach to this whole topic, and we even asked ourselves, should we really do this again? But yeah, I mean, it seems to work out, so that's quite nice.
In the end, it's all about nice samples.
I've heard this somewhere in a podcast before. It's about the input data, the preparation. There was one question. It's like one on our team was asking, why are they not entirely stable? Those, and it was, I think it was from a perspective of using another text to image environment, and the complaint was that every time when he tries to do some evolvement there, it permanently changes entirely. He can never grasp it. I think it was like a step up or something, like you improve the resolution or something. It has not something entirely to do with stable diffusion, but I just throw this question in here. Is there some aspect of chaos in there when it generates those images? Maybe that's the question.
I mean, there's certainly the aspect of randomness in it, right? Because it's a generative model that has learned this probability distribution, and then if you given the same text input, the model gives you the distribution around that text input. If it's a very, very, very specific text input, then that distribution might be narrow, but it's still more than like a single example. And if you don't fix your random seed that you use to generate the first one, then I guess this is like one of the explanations. Maybe I'm not understanding the question correctly.
Is there or another perspective? Is the word stable diffusion, the stable in the diffusion, is that a coincidence with the company that brought it out, or is it has it a meaning in this specific software?
It was completely like internal working title for that project because of the company that funded it.
Okay.
So I mean, yeah, up to interpretation.
Okay. So let I go back to the question that I would follow up with. The democratization part, it runs on every computer. It kind of probably through that screams for a certain kind of publication, but unlike other companies out there, that you know, who knows why, do not publish everything open source like you do. What is, from your perspective, what is your motivation or behind publishing that open source? Like, you probably could have. I think actually I listened to a podcast from the CEO from the Stability AI, and I think there's a lot of business behind that. So I wouldn't want to say like, hey, you couldn't take a lot of money and do it differently. I think there's a lot of good business model in open source, but is there like a specific perspective that you have on open source with this work?
Yeah, maybe I can kind of explain it from my perspective, like how I perceived it through my PhD. So when we did this work on taming transformers and VQGAN, we already open sourced the VQGAN model. Nobody really cared about the transformers that we've trained. They were also like university budget, so not too powerful, right? But that VQGAN model, it really I know was used very widely in the AI art community, and there were so many interesting projects like combining our model with Clip, the OpenAI model, and to actually generate art or images from text already. Was a very different approach than what is used today. But it was, for me, it was super inspiring actually to see that wide adoption of, like, you train something that works fairly well, and then you just open source it, and then people can just use it for whatever they like. And I found this very inspiring. And I don't know, this is maybe for like my personal explanation for it.
Nice. You know, I don't want to go too deep into it. I mean, of course, it's very controversial whenever you bring new technology out. But so I have the really interesting situation. My mother is an artist, so she is one of those, perfect guinea pigs for putting her in front of this technology. And I wanted to see what she's doing with it. And the first thing, she dropped her art in. She gets variations on it. She gets inspiration from it. She starts immediately using it as a tool, expanding her work. And the end of the session was, can you send me all of that? This is really interesting. That just gave me a lot of ideas to continue on some work. So it's really interesting, to see that your perspective on, it's a tool. It helps people to transform ideas.
Yeah, absolutely. I guess in the end, that's saying that like the only border is the imagination. I think that is probably true, not yet for the models that we have, but maybe in the future. And I like this very much. That's very cool.
It's interesting how it touches what imagination is. I think about this quite often. When I look at this kind of technology, it's like, what is it actually that when I imagine something, in my mind, when I create something, what is that process of imagination actually? Because you could say your software is imagining things, and we imagine together. The computer and we start imagining together.
Yeah.
So you have
maybe
this,
one nice feature is actually, I mean, it is a tool that can help artists to create better or different art. But on the other hand, you don't have to be an artist. You don't have to, you don't have to go through an intensive education, and you can still visualize your imaginations extremely quickly. And I think this is a very nice thing that didn't really exist before.
Yeah, it's like, if you can't draw, then all your images are stuck in your head. How do I get them out?
Yeah, I mean, you can talk about it. There's different stuff, but yeah.
But sorry to interrupt, but another really nice thing, it was like I think a Japanese publication, which visualized, I think from people who were not able to speak, visualized, they built a brain interface to a text model, or to a text input, and then they visualized thoughts actually, which is also really great, because you can also help like impaired people, or I think this is also really great. But as you said, this is just another like application of this model as a tool which can actually help humans.
Yeah. So I'm jumping in my questions again, because this is something I think is interesting that we're getting into. It's kind of like a prosthetics for imagination. And when we think about the metaverse, there's a lot of interesting environments. Like, I looked into VR chat or something like these things, and people build their own stories, and then they bring friends into their stories, and they have really interesting environments. It's almost also children, they imagine stories, and then they play in them and live in them. And the technologies that you build, I can imagine from what we are talking here in the moment, it's like you can get into a world. You can literally use it for world building, right? You can tell them like, I want the environment around me look in a certain way, and check, it comes up. You don't have to work for weeks to draw the paintings. You just start imagining the world around you, and it becomes a virtual, a metaverse reality.
Yeah. I guess there's some work to be done to make this work for, I don't know, like these 3D scenes that you're probably thinking about. But I like that perspective. And also, maybe another way to think about these tools like Stable Diffusion or other text-to-image models is by using them, you are actually, I think, because this stuff is available, people in general can just get used to that technology, and by using it themselves instead of this is how it has to be used. And I think this is also a very important aspect of it.
Yeah, that's an interesting thing of open source. I'm a big fan of open source. Like when I crowded here in the media lab, all my work was open source, and I still push open source in my role where I work. And what is the really interesting thing is that the way that people start taking your work, making something you have never expected. Like it's the most fulfilling feeling, you know, when you see your work in the hand of others and suddenly it turns into something that you have never imagined. I mean, in your case, the work itself creates things that you would never imagine would happen, but you know, it's kind of like a double thing. But what are the kind of, you already mentioned some text to image interfaces for impaired people. What other really interesting or other really interesting projects have you seen, like transformations of your software or teams that expand your source code and bring it into something completely different? Like what are the really impressive, interesting ways or surprising ways that you see your software being used?
So I think one really cool thing, which was actually really fun that it worked out, was Diffusion. I don't know if you've heard about that. Basically, they fine-tuned Stable Diffusion on those spectrograms of Fourier transforms. So you can visualize them and visualize the harmony spectrum. And they just trained or fine-tuned Stable Diffusion on those images in the end then. And by using an inverse Fourier transform based on the images the model then was trained to create, they could just like output really nice music actually. So this was really, really cool. I really love music also. And yeah, it was surprising. It was, so we had like within the last few months, we had a couple of also powerful audio models which actually worked on audio representations and not using this tweak to just like create images, and by using Fourier transform back to the music domain. But it was so fun that it was like out of the box generating music, which before was, I'm not an expert in audio modeling, so I don't know, but I think it was like pretty decent compared to what was there before, and this was really impressive, I'd say. Another thing is just like many applications which are like popping up, which are not like specifically based on Stable Diffusion, but on latent diffusion models, such as protein design with those latent diffusion models, which is really cool, or cryo-EM structure design and whatever. So other domains, because this formalism of having an autoencoder and the diffusion model, or some generated model in general, diffusion models are just like, as said before, because of their flexibility, quite nice, I would say. But this first stage autoencoder is kind of imagined as a domain expert, which can be applied for principally any domain. And then training an autoencoder, people who have like trained neural networks would probably agree that it's like you first, when you do some course on neural networks, you first train a classifier, and then you maybe the second thing will be an autoencoder or something. So it's really it's not hard to train that. Sure, you have to do much optimization if you want to get really nice results, but it's like a principled way to model data. And in the autoencoder, we could model some I don't know, domain knowledge, expert knowledge, and then just have this diffusion model, which we know it trains stably. It's like it is for most data domains. It's really yielding powerful results. And yeah, so this is like a principled way, I would say. And whenever I see something new, I'm like, yeah, cool. It's like it's also working on that domain. Nice. 3D modeling, it was also applied to, I think, on point clouds. Also quite nice. Yeah, Robin can probably add much more on that.
Yeah, maybe another nice thing is just the speed of innovation, or like the parallel innovation that's happening. Like since the model was released, there was so many follow-up works and so many tweaks. Like some, maybe you've heard of control net or stuff like that, where you add additional control to stable diffusion in the form of, like, I don't know, you can draw a stickman and then it generates a human in that pose, stuff like that, or making inference more efficient. I actually, like, after we published the model, I actually went on a holiday and I had like one paper in mind where I said, hey, I want to implement that for stable diffusion when I come back, and then it was already done. And like, yeah, and this was just the beginning. There's so much stuff happening because it is accessible, which is, yeah, it's super nice.
Yeah, I have to say the work with the music and the control net stuff, I think this propagated through our Teams chat in my team. And everyone like, whoa, you know, there's a lot of wow going on right now with all of these updates. So, hey, we're starting to run a little bit out of time. I want to ask two more questions to you. One, and then we open up questions into the class. One question is, like, if you would have unlimited resources, you know, if there would be no limitations, you could hire as many people as you want, whatever it is that you would consider a limitation at the moment, like what are your dreams? What would you want to realize? What is your vision that you want to bring forward that you're curious about right now? It's a tough, actually a loaded question now that I asked it.
It's a very tough question. So if we restrict that to media synthesis, like that we could use the resources for media synthesis, then I think this is something that we've talked about for a while, like training a powerful multimodal model, like not only text, not only images, but other representations, would be super interesting. And actually, it might make like something like a language model more grounded in reality if you add other types of signals and paired data. Something that I personally want to see, which is not like in the media synthesis, but maybe applying this kind of techniques to stuff like I don't know, like numerical weather prediction. I find this very interesting and also impactful. And I think this is underexplored right now. There are a few works which try to use generative models for that, but yeah, all the hype is on generating media, images, videos. But yeah, I think that there might be some of these applications, but where you can really save cost of rerunning numerical simulations by actually training a generative model once and then using that.
Basically, for every kind of physical problem where we have some like models we know are not accurate enough to make good predictions. Whether it's such a thing that there are, I mean, for chemistry, generative models are already like quite widely used, I would say, AlphaFold and the like. But yeah, all those like problems in natural science, we always have models which are like most of the time partial differential equations or whatever. And we always know that we have this modeling error and generative models. So and that's why people account for like uncertainty in the model and want to tackle that out. But once you have a generative model, you don't this naturally models your uncertainty, and you don't need a really complicated system of like model equations anymore. This is really a nice thing, I think, which in the future might like make the humanity profit a lot from it, I would say. So this is like thinking a little bit further. Whenever you have the data to train these models, and for physical science we have many or like much data, it's worth a trial, I would say.
Cool. Okay, we run way over time. We'll get some questions in from the class as well. First of all, I want to really thank you guys to visit us virtually, and I'm looking forward to follow you throughout the years and see where your journey is going. So, oh, and also there were questions. You mentioned some papers here and there. I will bug you afterwards with like maybe you can share some of the papers that are interesting and we share them with the class. Yeah. Okay, hello classroom. Do you have some questions?
I have a good question.
Could you come up here because the audio?
Oh, it's yeah. Okay. Can you guys hear me? Oh, it's distracting me. Hello?
Yeah, very well.
Yeah, I'm just curious. Could you talk us through the study you did? I think it's like figure 2 in your paper, one of your original papers about the semantic and perceptual compression, where you looked at the trade-off between the two. Could you explain your findings there? And is there other literature that you'd recommend looking at?
Yeah, that's a good question. I think the figure that you're referring to, it's mostly like a motivational figure, and it's actually from the DDPM paper. It's a bit adapted. So we use that to kind of motivate what I've also been talking about, that there's like, if you model natural image data, the model has to allocate like, let's say 90% more of the bits to that high frequency data that doesn't really impact how we perceive the image. And diffusion models actually offer you a way of visualizing that pretty nicely. So because you can decode from arbitrary steps during the denoising process, you can basically visualize the difference between like the input data and what happened after step 1, step 2, and so on until the final step, let's say 1,000 steps. And what you see in that plot is that in the beginning, where like the majority of bits is allocated, we don't perceive a difference in the generated output. And then if we go into, and we can measure that amount of bits by measuring likelihood, which diffusion models offer us. And then if we move further along that diffusion axis, then we see that for the final amount of bits the semantics change very much, and this is kind of this distinction that we made, and also that other authors like Jonathan Ho made in their DDPM paper, between this like semantic compression and the more like the
conceptual compression.
Any other questions? Because I have sorry, no, you go.
I just had a quick question in regards to, you mentioned briefly some of the new connections with ControlNet in Stable Diffusion, and I was just wondering if you feel like as these models get better at generating images, if we would be able to get some higher accuracy with just text as we get better, or is something like ControlNet, we have other means of input rather than just text, kind of important in really mapping out that complete picture, right? Is there, I think we talked with Jaron and Lanier about like kind of the post-symbolic ideas of like, what are the limits of just using language? And I was wondering if you had any thoughts on that.
I mean, yeah, in general, if you add more information, which is like complementary to the ones you already have, then the model will be able to like come close to what you imagine or what you envision, or come closer to what you envision in general. So if we text, for instance, we take text that describes some scene, but you have to be really specific in your text in order to get a really detailed description. So we one sentence is usually not enough, right? We can make a long sentence, but to really completely describe a scene, also with all the spatial arrangement and whatever, we really need to go into detail, right? And we could do this, but in some sense, we will at some point reach the limit of our text encoder, basically, of what our text model is capable of doing. And for Stable Diffusion, since a very like cheap text model was picked, this limit is actually reached quite, compared to other text models, quite fast, I would say. And therefore, it's just like cool to get more control by adding additional conditioning domains, so to say. As for instance, if you use this like stickman again, you perfectly define the posture of the person you want to create. If it's like a person, can also be another model, but you give some idea of the shape you want to generate to the model, and any information which is like beneficial to its training task, which is basically like generating images, the model will incorporate it in some sense, and this is what happens. So and we could ask, we could add more information and the more information you add, which is, so it should not be like redundant. This will give us nothing, but as long as it's like complementary and adding new information to what we have or had before it, the model will always make use of it. And by adding more and more and more, we could go as far as adding the image itself. Then we could visualize what actually are the model which encodes our image, because we have to encode it in some sense. Then we would reach that limit of visualizing what is in our encoder, which is also quite interesting, I would say. This is actually what Unclip or like DALL-E 2 in this diffusion model training does without the prior. I don't know if you know the paper, but they're basically learning to create images based on clip text embeddings. And by this, you can visualize, okay, what is preserved of this input image in clip and what not. So you can visualize invariances in clip, which is, it's a lot of fun to do that. But yeah, I sorry, this was maybe a little bit too wide. Hopefully I answered the question. Okay.
Maybe something else to add is, it's actually interesting that we observed these like all these fine-tuning applications, and I think this hints at the fact that the published version of Stable Diffusion is not powerful enough to do all the use cases with just text. So there is the question of whether we will have like multiple models, control net style models, like small models in the future, or the other approach is we just have like a text image model, right? And because the promise of text to image is that you can just describe anything with text and then it should do that. So maybe for very large text to image models, we will see that, but for the smaller ones, this additional information is super helpful.
Kathy, I think you had a question as well, and I think we run out of time with the question as well. So yeah. One last question or two.
If nobody else has a question.
Okay.
I think just to follow up on the thing that Drayden just asked about additional other kinds of inputs, and could you speculate a little bit about creating three-dimensional or even interactive spaces, how maybe your model and combining with other types of models could help make this happen, so that people can not only just see images, but also maybe project them into a 3D world, interact with them in some ways. If you could help us like envision that future.
Yeah, I mean, this is a very open question, right? It's ongoing research, super hot topic. We have seen, I think one line of very interesting work is extracting 3D knowledge from these pre-trained text image models. So, I mean, Diffusion does that implicitly by optimizing for a scene. There have been other works like recently one work that is called 0123, which actually takes Stable Diffusion and fine-tunes it into a novel view synthesis task. And then there have been other works. So there's a work from NVIDIA, which learns a 3D encoder jointly with the diffusion head and incorporates like explicit 3D modeling in that 3D encoding process. Something that we are very interested in is extracting that knowledge from pre-trained models. And I mean, we have image models, but we also have we'll extend that. I mean, there's video, stuff like this. So maybe combining all of these gives you even better representations already.
Okay. Thank you so much for taking the time and visiting us virtually.
It was a pleasure to be here. Thank you.
Wonderful. Have a good evening.
Yeah, thank you. Have a nice day. Bye-bye.
Bye-bye.
So for everyone in the class, we'll take 10 minutes, 15 minutes break and be back at 4 p.m. And with our next speaker, Matthew Tanzik, and one of the authors of NERF. See you later.